Hello, and welcome to this presentation demonstrating UPC++ and Cocos interoperability in a heat conduction simulation. My name is Colin McLean, and my co-authors on this paper were Daniel Waters, Dan Bonacia, and Paul Hargrove. We are members of the Applied Mathematics and Computational Research Division at Lawrence Berkeley National Laboratory. Together we work on the Pagoda project as authors of UPC++. The Pagoda project exists to support lightweight communication for exascale applications, frameworks, and runtimes. The GasNet-EX library provides a low-level, network-independent interface to interconnects suitable for partitioned global address space or PGAS runtime developers. This GasNet-EX library is used as a networking backend for several projects, both internal and external to the Pagoda project, such as CoRay Fortran, Chapel, and UPC++. UPC++ is a C++ template library for application, framework, and library developers as a productivity layer over GasNet-EX. It leverages modern, sophisticated C++ template metaprogramming internally to provide an efficient and productive interface to our users. UPC++ is designed to be used both in intermediate libraries and directly in applications. So here's an overview of what UPC++ offers the programmer. First, there is RMA, by which I mean puts, gets, and atomic updates on locations in the global address space that might actually reside in the memory of a remote process across the network. These operations are semantically one-sided, in that there's no corresponding receive operation executed by the passive target process. Where appropriate, these leverage RDMA offload support in the network hardware, so that the remote CPU is often not even involved. The other flagship communication operation in UPC++ is remote procedure call, which induces a potentially remote process to perform some computation on our behalf and optionally return a result. The UPC++ interface follows three major design principles. First, all communication operations are syntactically explicit, which encourages programmers to consider the costs associated with communication and data movement. Moreover, all communication operations are asynchronous by default, encouraging programmers to seek opportunities for overlapping communication latencies with other useful work. UPC++ provides expressive and composable abstractions designed for efficiently managing aggressive use of asynchrony in programs. Finally, UPC++ encourages the use of scalable data structures and avoids non-scalable library features. So here's a quick introduction to how RMA operations look in UPC++. The library provides a template called global pointer, which is an abstraction representing a pointer to a location in the global address space, in this case an object of type int. Here we'll assume that the pointer has been initialized to reference an int variable living in the shared segment of a remote process. The UPCXX rget function initiates an RMA get operation to retrieve the value of that variable. Now, you'll notice that this function does not return an int, because this is a split-phased operation. Instead, it starts an asynchronous get operation and returns a future of int, where a future is an abstraction representing an int value that may or may not be ready yet. The future encapsulates the result of an asynchronous get and readiness state. Once we've launched our get operation, we can proceed to perform unrelated work overlapped with the communication latency. Eventually, we later call the future.wait function, which stalls if necessary, to wait completion of the communication, and then returns the retrieved value. If you're familiar with old Cray architectures, you can think of the future abstraction as analogous to full/empty bits, although futures are actually a lot more powerful, as we'll see coming up. But this demonstrates the basic asynchronous structure of RMA operations in UPC++. Next, we'll take a look at the RPC operations in UPC++. So the basic idea here is an initiator process wants to send a function call and some arguments to execute on another process, using the resources available at that target process, and optionally return a result. The initiator makes a UPCXX RPC function call that specifies the rank of the target process P, along with a callable function and some arguments. That call injects an RPC designated for that target process, and immediately returns a future to the initiator representing the asynchronous completion. The RPC carries a reference to the callback function and a copy of the arguments, which travels through the network to the target process, where it will execute the specified callback function with the provided arguments. The return value from that callback function is sent back over the network to the initiating process. It is that result which lands in the initiator's future, where the RPC return value is now ready to be consumed. Next, I'd like to expand on how UPC++ enables aggressive asynchrony for overlapping communication latency. As we just saw, UPC++ communication operations like RMA and RPC default to returning a future object representing an asynchronous operation in flight. This enables simple overlap, where we later wait on that future to stall until the result is ready. However, we can alternatively do more interesting things with futures. For example, we can use the future.then operation to schedule a callback to automatically run on this process when the future is readied. That callback can then issue additional asynchronous work, leading to a chain of asynchronous operations. We can also conjoin multiple futures together using the whenAll operation, which creates a new future representing the readiness and results of all of its inputs. Together, this enables us to concisely build arbitrary DAGs of futures representing asynchronous dependencies between communication and computation, where the vertices in the DAG are automatically executed as dependencies become satisfied. In the example here, we launch two RMA get operations and can join their futures together using whenAll. The resulting future is then used to schedule a callback that will then run after both gets have finished and combines the results into a value that is then asynchronously put into a third location. The result of this scheduled DAG is itself a future, fut2, which represents a synchronous completion of the entire set of actions. UPC++ is designed as a one-sided programming model using futures and continuations to handle asynchrony. Communication is based upon remote procedure calls and RMA operations through the use of global pointers. UPC++ supports remote atomics and non-contiguous RMA. The serialization and distributed object interfaces allow for the communication of non-trivial C++ types, enabling the full-featured use of C++ across address space boundaries. Teams and non-blocking collectives are available for collective operations. Hierarchical shared memory and node-level bypass are used to optimize communication between processes within a node. Recently, UPC++ added support for memory kinds, enabling efficient communication of GPU memory. UPC++ interoperates with other programming models, which will be demonstrated later in this presentation using UPC++ for parallelism between nodes and Cocos for on-node parallel execution. UPC++ is a production-ready library. Applications across disparate domains have been written using UPC++, resulting in both improved programmer productivity and runtime performance. These include MetaHitmer, a genome assembler, SymPack, a sparse symmetric matrix solver, Pond, an actor-based shallow water simulation, SymCove, an agent-based simulation of lungs with COVID, and MELUPX, a half-approximate graph matching solver. UPC++ RMA operations utilize remote direct memory access support when present in hardware. RDMA is an important performance feature in all modern HPC networks. GPU Direct technology extends RDMA to GPU memory. UPC++ memory kinds extends the PGAS model to encompass GPU memory. In UPC++, the distinction between host and GPU memory can be encoded in the global pointer type, permitting constant evaluation of the appropriate code path for communication of a memory buffer. CUDA-aware MPI implementations lack equivalent static meta-information. The purpose of this paper was to demonstrate the interoperability of UPC++ and Cocos. Cocos is a C++-based framework for performance-portable on-node parallelism with the ability to leverage heterogeneous compute resources such as GPUs. UPC++ complements Cocos as a C++ library for multi-process and multi-node parallelism. The heat conduction program used for this demonstration is based off an example provided by the Cocos project to demonstrate its interoperability with MPI. Because the MPI message passing used in this example is a two-sided model, there is not an apples-to-apples comparison between the MPI and UPC++ implementations. However, the goal of this demonstration is not to prove performance superiority of UPC++, but rather that the sophisticated features of UPC++ do not come at the expense of performance. The heat conduction example computes heat in a three-dimensional cube using halo exchange between neighbors. This example was ported to UPC++ without prior experience interoperating with Cocos. Both the MPI and UPC++ versions of this example were written naively, without excessive effort put into optimization. The ability to reach close to peak hardware performance in a finely tuned application is not at question, but rather what happens when the code is written in a simple, maintainable, and productive manner. The heat conduction example has 6 main steps for each time step. First, the data in the halo region of each local cube is packed into buffers for exchange. Then, computation of the interior movement of heat is dispatched. Meanwhile, exchange of the halo data between neighbors is started. Once this communication has completed, computation of the surface of the cube is performed. The program then waits for the computation of the interior to complete. Finally, an average temperature value for the local cube is computed. To port the communication of halos from MPI to UPC++, the exchange T halo function must be modified. The following communication happens between each of a node's neighbors in the MPI version. First, a fence operation ensures that the copying of data between the cube and halo buffers has completed. Then, non-blocking sends and receives are posted. The communication stage finishes once waiting on all communications has completed. The UPC++ version of communication replaces the sends and receives with a one-sided copy of buffers. By attaching a remote procedure call to the completion of the RMA operation, the receiver is notified that the buffer is ready by incrementing the count of received halo pieces. Once this count reaches the expected number of received buffers, communication for this time step has completed and the execution continues. As one can see, this is not a complex modification. The pattern differs in that MPI is two-sided, while UPC++ is one-sided, but the ability to attach completions to RMAs results in the synchronization not being any more difficult. Additional modifications must be made to the setup of the GPU memory buffers. First, UPC++ needs to interact with GPU memory using its own memory kinds interface. This is because the host versus GPU memory type is statically known as part of the type information with UPC++. A UPC++ device allocator allocates a large GPU memory segment and registers it with the network adapter. From this, partitions are assigned to each halo memory boundary region. A non-owning Cocos view can then be constructed from the raw pointer to this memory. This aspect of interoperability could potentially be streamlined in an effort between Cocos and UPC++. Because UPC++ is a one-sided model, the remote pointers must be communicated. A similar modification would need to be made to use one-sided MPI. In UPC++, this is accomplished by the use of a dist object providing a universal name for the contained pointer. This idiom is demonstrated here as written in UPC++. Benchmarks were performed on the Oak Ridge Leadership Computing Facility's Summit supercomputer. Each of Summit's nodes has 6 NVIDIA V100 GPUs. One process was used per GPU to fully utilize the GPUs of each node. For the MPI version of the heat conduction example, the IBM Spectrum implementation of MPI was used. For the UPC++ version, a GPU Direct RDMA-enabled build of UPC++ was used. All benchmarks for each node count were executed within a single job to minimize variability of network performance. Each run of the heat conduction simulation executed 500 time steps, not including warm-up iterations. Timings were measured using a sliding window of 2 time steps. This was done because load imbalance can result in the early arrival of incoming data, and a sliding window ensures that at least one network operation occurred. These 2 graphs show the mean time per step taken in the heat conduction example. The solid lines represent the UPC++ version, while the dashed lines indicate the MPI version. The problem sizes are given by side length. The number of elements for each problem size is thus the cube of this number. The graph on the left displays performance characteristics for small problem sizes, while the graph on the right displays those of large problem sizes. 2 graphs were used to more clearly display the asymptotic behavior exhibited by both UPC++ and MPI implementations. Some lines are displayed in both and are given in the same colors in each. Our goal for UPC++ had been performance on par with MPI. Instead, what we saw was a significant performance improvement over the MPI version. At large cube sizes relative to node count, UPC++ performance matched MPI performance. However, the UPC++ version exhibited better scalability and performance as node count increased and the message size decreased. For instance, a cube of 400 elements aside reaches maximum performance at 128 nodes with UPC++, but suffers from decreased performance with increased parallelism with MPI starting from a single node. In an attempt to examine why MPI and UPC++ diverged so greatly in performance, we looked at a histogram of communication times. This figure is representative of the phenomenon occurring. The problem sizes are shown at 128 nodes, 800 cubed and 6400 cubed. The vertical dashed lines in the figure indicate median time per step. MPI suffers from a large number of slow outliers. Some of this phenomenon may be explained by the two-sided nature of the MPI version. If the networking step of the computation were split into two phases for MPI, such that receives were posted early to be ready to receive data, this may improve MPI performance. This was not explored in the time taken to conduct this study, as the intent was not to compare tuned applications. This investigation may be attempted in the future. It should be noted that with a 6400 cube, MPI having a lower minimum may be due to early arrival of incoming data. In conclusion, we found that UPC++ can interoperate with Cocos without difficulty. Porting from MPI to UPC++ was likewise straightforward. The intention is not to prove superiority to MPI performance. Well-tuned usage of both should get close to theoretical hardware performance. The new UPC++ memory kinds feature was also found to be performing well. UPC++ has many sophisticated high-level features, but these can be attained without sacrificing performance. I would like to thank the Exascale Computing Project for funding this research, and the Oak Ridge Leadership Computing Facility for our use of the Summit Supercomputer. Thank you, and I will now take questions.